Hello students, so the next concept is on AVL trees. Earlier we studied about binary search tree and we understood how it makes searching more convenient. However, there is a problem with binary search trees in certain cases. For example, if the elements are of this fashion, say 55, 20, 19, and if we go further, say 18, 17, 12, 9, 1, etc., then you will see that it is almost like a linear linked list, right? We actually want something like a tree here, but unfortunately if the new elements that come are lower than the previous element, then it is always going to follow this fashion. And the opposite can also be true. If the new elements that get introduced are higher than the previous element, then it will always go to the right hand side. Okay, so in those cases searching becomes does not become that efficient. It almost looks like a linked list. So can we improve that? Okay, so this particular tree, which almost looks like a, not only almost, it exactly looks like a linked list, right? So if we want to make it a tree that looks something like this, we have to put certain operations on it. Okay, so these concepts will be understood in the next concept, which is AVL trees, okay, developed by Adelson, Welsky and Landis. So let us try to understand what AVL tree does, or how it tries to improve the binary search tree. So suppose we have a root element called A, and of course it is going to have a left subtree most possibly, and it is also going to have a right subtree most possibly, right? And in this example we assume that it has, okay, this root node has a left subtree and a right subtree. I think you have already understood the concept of subtree, right? So that means we can have a particular tree structure inside this A also, okay, and it can be empty also, which is known as which comes from the concept of empty trees. A tree may not have any nodes as well, but in this case, in order to understand it, we assume that yes, we have certain nodes in this subtree and in this subtree. Okay, so now what we have to do in AVL trees is we have to always follow this rule, and that is the height of the left subtree, suppose it is x, and height of the right subtree, sorry, it's mistake, height of the right subtree, which is maybe y. Then what has to be done is, if we find a difference between them, that is x minus y, the value must always be either -1, 0 or +1 in order for the tree to be an AVL tree. Okay, so we calculate the height of the left subtree, which is x, then we find the height of the right subtree, which is y, then we do x minus y, and whatever value we come with should always be either -1, 0 or +1. Okay, this difference is known as the balance vector. So this x minus y is known as the balance vector. So we can conclude that the balance vector must always be either -1, 0 or +1. Okay, so let us try to understand how to obtain these balance vectors and how to modify a particular existing binary search tree into a AVL tree, right? If the balance vector is not acceptable. Okay, so there are 4 rules that we have. Number 1 is left left, then we have left right, then we have right right, and then we have right left. Now we have to understand each of them, and this is what going to be taught in this coming slides. Okay, so here we have left left, which is LL, which is left right, which is LR, and so on, just the abbreviations. So if we have a left left case, then we are going to do a right rotation. If we have a left right case, then we have to make it left left and then make a right rotation. If we have right right case, then we do a left rotation. If we have a right left case, we do a right right and a left rotation. So let us try to understand what it means. So we take the first case here, which is left left case. So here we have this particular tree with us. We have 10, then 6, then 3, and then 10 and 15. It is a binary search tree. Yes, it first of all, it is a tree. Yes, we don't have any cycles. It is a tree. It is a binary tree. Yes, because every node has maximum two children. Sorry, because 10 has 2 children, 6 has 1 children, and 3 has 0 children, and 15 has 0 children. Right. So it's a binary tree. It's a binary search tree as well, because all the elements to the left hand side of 10 are lesser than 10, and all the elements to the right hand side of 10 are greater than 10. Okay, similarly if you look to 6 or 3 or 15, you will get the same principle. Okay, So how to find these values? Okay, so here we have certain values with us in blue color, light blue color. We have 0, 1, 1, 0. So how do you find these values? Now theoretically, it is basically, as we already know, x minus 1. It is height of the left subtree minus height of the right subtree, right? So this is how we get the values here. So you can always find the height of a particular tree and then calculate, etc. But in order to make things faster, what we can do is we can count the edges and get the values. So let us try to understand how we get 1. It is very simple. You go to the left hand side, you just take the node having the highest distance from this particular node. So 3 has the largest distance, right? So you start from 3 and you count the edges. So it is 1, then 2. Okay, so we have 2, and then so in the left hand side we have 2, and in the right hand side you have this only 1, because if you go to the furthermost node, then it is 15. Here it is only one element, so we have to take it. So here we have only one edge. So in the left hand side we had 2, and in the right hand side we have 1. So 2 minus 1 is going to give me 1. Similarly, for in this case, we have left side we have 1 edge, so it is 1. Then right side we don't have any edge, so it is 0. So 1 minus 0 is 1. Again, here we don't have any left or right subtree, so 0 minus 0 is 0. And in case of 15, we have 0 minus 0 is 0, because we don't have any left subtree or right subtree. Is it fine? So for any element, you can always find the particular balance vector associated with it. Okay, so now let us again go back to the definition. In the definition, it said that this difference or this balance vector that we find should always be, or sorry, must always be minus 1, 0 and plus 1. So do we have minus 1, 0 or plus 1 here? Yes, we have 0 and 1. So these values are permissible. Okay, these values are allowed. So we can conclude that this particular tree is a AVL tree. Okay, so now let us try to create some problem and try to solve as well. Okay, so we have 10, 6, 3 and 15. This is taken from here, but now a particular new element is introduced. Okay, so before even this happening, there must have been some sequence of elements entering the pipeline, and then accordingly one of the elements was, one element at a time was taken, and this particular tree was drawn, right? So what can be the possible sequence of elements that came one by one? It can be 10, then came 15, then came 6, then came 3. Okay, one sec. Okay, so how this tree was formed, or how this binary search tree was formed? So the possible elements can be 10, 15, 6, then 3, or it may be 10, 6, 15 and 3, right? So then what happens is, suppose a new element has joined, which is 1, and as we know, 1 will be compared with 10, it will go to the left hand side. 1 will be compared with 6, it will go to the left hand side. 1 will be compared with 3, it will go to the left hand side, and then add up to the 3, right? So the problem here is, once 1 is added, okay, with this 3, let's look at the balance vectors. Now the balance vectors will change, okay, because the heights will be different now. So what happens here is, if you consider a balance vector here, it is 1, 2 and 3. So and in the right hand side we have 1, so 3 minus 1 is 2. Again for 6 it is in the left hand side we have 1 and 2, in the right side we have 0, so 2 minus 0 is 2. Again for 3 it is 1 minus 0 is 1, 0 minus 0 is 0, and for 15 0 minus 0 is 0. Okay, so now do you see the values here? The values are 2 and 2. Okay, others are fine. 1 is permissible, 0 is permissible, 0 is permissible, but what about this 2 and 2? Somehow we have to make it within minus 1, 0 and 1. So what we do is, we try to go to the element which has been newly added. So we go to 1, and then we take a journey to the root of the particular tree. Okay, so the root is 10, so we take a journey from this new element up to the root. So as we move, as we go forward, there will be a point here when we will realize that the balance vector is not permissible. Okay, so as we start a journey from 1, 1 has 0, so I move forward. 3 has 1, so we move forward. Then we have 6, where we have the balance vector is 2. Now there is a problem, right? We cannot accept 2, so we will stop here. Okay, and we will take the 3 elements from 6. Okay, because we stopped at 6, so we will come backwards and take the 3 elements. So 6, 3 and 1. Okay, it is very simple. So you just take a journey from the new element that has been added up to the root, but you will stop maybe at the middle of the journey if you find a node with a imbalance factor. Suppose it is 2 here. So what we will do is we will again try to go back 3 elements. So it is 6, 3 and 1. So now we have a particular small tree with us which looks like this. We have 6, 3 and 1. Now since this is a left case, right, that's why this particular case is called left case, because the imbalance scenario happens for a left and a left tree, okay, subtree, okay, left and a left. Okay, so whenever we have a left and a left problem, what we have to do is we have to do a right operation. Okay, so here you can see we are trying to rotate it in the right direction. Okay, so here we take a right rotation. So it is something like you just try to rotate this particular structure. So when you rotate it, it will look something like this. So 6 will come to the right hand side, 3 will come to the middle and 1 will come here. Okay, you just try to visualize the rotation. You just try to rotate it to the right hand side, okay, and then make a small bend, and then it is going to look like this: 1, 3 and 6. Now if you look carefully, this is also a binary search tree. So there is no problem, because here we had 6, 3 and 1. This was a binary search tree, fine, with a skewed nature. Anyways, then we try to do a right rotation, and then it again maintains to be a binary search tree, because 3, 1 is smaller and 6 is greater. Okay, so it is fine. So now once we have rotated it, we will just join it to the place from where we detached it. So we detached the entire structure here. So we have taken it out, we have rotated it, and now this 3 is going to be joined here in place of 6. So earlier, as you can see, we had 6 here, but now after detaching it and rotating it, we are going to fix it again. So we are going to fix 3 here. Okay, because as you can see, 3 is in the what you call higher, or rather we should say lower level. So 3 is like a root here, right? 3 is like a root here for a small subtree. So what we do is we take the root of the subtree and try to join it to the place from where it was detached. All right, so once we do this rotation and try to see the values here, what we see is we find the values 1, because 1, 2 minus 1 is 2 minus 1 is 1, then 0 minus 0, 0 minus 0, 0 minus 0, and this is 1 and this is 1. So 1 minus 1 is 0. So all these values are permissible, and thus we can say that though this was not an AVL tree, with the right rotation we have been able to obtain a AVL tree. Okay, this is one of the cases. This is left case, because we find a left imbalance. Then we go to the next case, which is left right case. So suppose we again had those elements 10, 6 and 3 and 15, and the new element is 4. In the earlier example I showed it with a lighter blue, but here I just forgot to change it, but assume it to be a lighter blue. Okay, because this element has been newly introduced. All right, so once we newly introduce this particular element to the tree, the balance factor is not permissible, because we have 0, minus 1, 2, 2 and 0. Okay, I think you already know how to calculate the balance factors now. This is minus 1 because in the left hand side we have 0 and right hand side we have 1. So 0 minus 1 is minus 1. Okay, so now again we take a journey from the leaf or rather the new node that has been added up to the root, but we will stop in the middle if we find a node where we have a imbalance factor. So here we have 6 has 2, so we have to take it from here, and then again take a return journey for only 3 elements. In this example we have only 3 elements specifically, so we will go up to the end, but at certain cases it may happen that you have to take 3 elements and you can go further, but you will not. Okay, so you take a journey from the leaf node up to the imbalance node, and then you take a return journey for 3 nodes. Then you take it out, so 6, 3 and 4 has been taken out. Now this is an example of left then right. Okay, that's why we wrote left right case. This is a left right problem. So what we do initially is we try to make it linear. Okay, in the beginning we will try to make it left because as you can see here, if it's a left right case, then we first do a left then we do a right rotation. Okay, so first we are going to do a left. So if you have to do left, you cannot make bring 4 from here to here, right? You cannot do that, because then it will not be a binary search tree. So what you do is you try to put 4 in the middle. So 4 is going to jump between 6 and 3. So 4 is going to jump between 6 and 3 will come down. So now it looks left now, and also it's a binary search tree. Okay, so you have to always maintain the properties. Fine. So just remember this way, if we have an angle disbalance, then just bring the last element to the middle of the earlier tree. Okay, whenever you have an angle. Okay, so here we had an angle, so we shifted 4 to the middle of 6 and 3, and it becomes 6, 4 and 3. Now it is a simple case of left case, so you can just make a right rotation and it will become 3, 4 and 6. So we just take it, okay, and then try to bend it to the right hand side. So when you do it, it becomes like 3, 4 and 6, where 4 is the root of the sub tree here. Okay, so we will just take 4 and join it to the place from where this entire tree was detached. Okay, so we put 4 here and it becomes 3, 4 and 6, and then we have 10, and then we have 15. So now if you calculate the balance factors, you will find that the values are permissible. We have 0, 0, 0, 1, 0, and it's an AVL tree. Okay, so this is a left-right case. Then we go to a right-right case, which is very similar to the left case. So what happens is, again we had these elements here, and then a new element called 35 was introduced. So once 35 was introduced, the balance factors will not be acceptable anymore. We have -2 here because 1 minus 3 is -2, then 0 minus 2 is -2, then 0 minus 1 is -1, 0, 0 is 0, and 0, 0 is 0. Okay, so that's why we get these balance factor values. So once you get it, again do the same thing. You go to the last element that has been added, and you take a journey to the root node, but stop if there is a imbalanced node. Then you again take a return journey for 3 nodes. You get 15, 25 and 35 back. And then since it is linear already, so you just do a left rotation. You try to rotate it to the left hand side and bend it, so it will become 15, 25 and 35. Okay, so you have a root node for the subtree here. You join it from where it was detached, so it was detached in 15, so you just join it here again. So now you have to join 25 here in place of 15, and then you get it. Okay, so here you can see that it is again a binary search tree. We have 6, 10, 15, 25 and 35, and also it's an AVL tree because the values are fine. We have 0, -1, 0, 0, 0. Okay, -1 is also acceptable, 0 is also acceptable. This is the right case. And finally we are going to go for a right-left case. So I think you already have an idea now. It looks similar to left-right case. So here we already had these elements 10, 6, 15 and 25, and now we add a 20 to the tree. Now once you do it, you calculate the balance factor values, you will find that these balance factor values are not permissible. We have -2 and -2. So now again you take a journey from the new element that has been added up to the root. You stop if you find a node where you have a imbalanced node, and you take a return journey for 3 nodes, and then you get 15, 25 and 20. So whenever you get an angle, what you do is you take the last element and put it in the middle of the earlier 2, as I told you before, right? Because whenever you have a right-left scenario, you always have to first make it right, something that has been drawn here, right, then you take a left rotation. So whenever you find something like this in an angular shape, then you first try to make it linear. So to make it linear, the easy way to remember is you take the last element and put it in the middle of the earlier 2. So we have 15, 20 and 35. Now once you have it, you do a left rotation. So when you do a left rotation, you rotate it and bend it, it will look like 15, 20 and 25, and 20 is the root node of this small subtree here. So you take it and put it from the place where this entire structure was detached. Okay, and finally we have an AVL tree here. Because it is a binary search tree, every node has maximum 2 child, then there is no cycle, it's a tree. It's a binary search tree, so it's binary because every node can have maximum 2 children, right? So apart from being a binary search tree, it is also a AVL tree, because when we calculate the balance factors, we find that the values are permissible, which the permissible values are 0, -1 and +1, and in this case we have 0, -1. Okay, so this is all for today. So we are going to continue in the next class. Thank you.